Okay, so the equation for momentum equals mass times velocity, and both velocity and mass are vectors. Conservation of momentum is true in all isolated systems in physics. A system is isolated when the net force is zero. In other words, if you add up all the forces acting on all the objects in the system, they add up to zero. And we know net force equals change in momentum over change in time, where both force and momentum are vectors. And multiplying through by change in time gives us the change in momentum of the system equals zero, and delta or change in always equals zero, equals final minus initial, and we can add the initial momentum of the system to both sides to get the initial momentum of the system equals the final momentum of the system. This concept is called conservation of momentum. The equation is usually written as the sum of the initial momenta of a system is equal to the sum of the final momenta of the system, when momentum, of course, is a vector. I will now use a skateboard and a medicine ball to demonstrate conservation of momentum. So, as you can see, when I toss the medicine ball, I move on the skateboard. This is because momentum always wants to equal zero. If we pretend the left is negative and the right is positive, when I throw the ball to the left, the system becomes negative and has negative momentum. And because it always wants to equal zero, I move to the right or to the positive. So my momentum, which is positive, cancels out the momentum of the ball, which is negative. And now the system is at zero. Now I will show you an example of the transfer of momentum. Okay, if we remember back to the equation of momentum, which is mass times velocity, we can see that the rubber ball has more mass than the tennis ball, which means it will have more momentum. This momentum is then transferred to the tennis ball by giving it a larger velocity, and this is why we can see the tennis ball shoot off the way it did. My last example will be on angular momentum. So here you can see when the weights are out, I move slow, but when the weights are in, I move faster. This is because I have reduced the distance between the axis of rotation and my mass. Now, because the angular momentum is conserved, my rotational velocity must increase to compensate.